Hey, there we go. Yep, that looks like it's working. Alright, so I'm gonna say we got a stream on our hands. Let me just announce it and then I will jump right in. Um, One other thing. Yes, that is working. Brilliant. There we go. Okay. Alright, so, oh, I actually want to check something else. Alright, so there we go. So, thing one today is I want to add in rotation. Rotation to the right, rotation to the left. And that's what this is the symbol for rotation. If you do it really fast, you just look like your fingers are wobbling around. Okay, so rotation in particular, what that means is we have this input sample. Let me pull that up. It's up here. Base image. Here it is. We have this base image going in, and I'm going to change the base image real quick. Let's make the base image look like this. And like that. And yeah, I don't really want that. Turn the debugging completely off. And there it goes, generating some rectangles with some paths in there, and it's cool. So the way it works right now, it's pulling its source samples from 3x3 images in here, right? And that means it gets a good number of samples this way. But if I wanted to add other features that might show up, for instance, and I messed with this a little bit last time, but for instance, if I wanted to add the ability to have like T-shapes, so what I'm going to do is first I'm going to rotate this. And since this wraps around the edges, so it doesn't matter if I rotate the image like that. And by rotate, what I mean is like shift, I guess. And what I want to do is add in the ability to have like T-shapes. So what I'm going to do is I'm going to make this 11 by 11, and we're going to have a row of 1s there and a 0 there, and then we're going to have a row there that matches the row above it, and then what we're going to do is have, so there's a T shape, and I'm going to have that come all the way out to here, and then bend up, right? And again, if I just go and rotate this whole thing 1 comma 1 comma like that, then pop over here, pull all of that out, and then 0 0. So we can see we've got in the top left corner a room, and then we have a corridor coming out of that room, and then it wraps right there and goes back into that room. Right here we have a corridor coming out vertically and wrapping back in at the top. And now I have this T-shape, but I only have a T-shape going to the right and a T-shape going down, and I have one elbow shape that is sort of like this. It goes up and to my left. I don't know if that's to your guys' left. Maybe I should. Yeah, so here you go. Up and to the left for you is like this, right? And so it goes up and to the left, and that elbow shape, which I'll show you what I'm talking about, the elbow shape that goes up and to the left. Where's my mouse? Oh, there it is. Right, there's the one going to the left, there's the part going up, just like that. And that means it only can make elbows of that shape because that's the only sample it has. Well, if I add in a rotation, what it'll do is it'll take every tile it sees, every 3x3 window, and it'll generate it as a sample, and it'll also take all 4 possible rotations and treat those as all possible samples too. Once it's done that, it can generate like rotated versions of this image from just the original. Now, that doesn't also include flips, which is probably something else I want to do, because there's certain cases where you maybe don't want to rotate, but you do want flips, and maybe there's cases where you need both to get everything. I think in this current situation, rotations, 4 rotations, so those would be fine. That right there would have 4 rotations. There's nothing here that I can think of that needs a flip. So we'll have to come up with a different test case for that. But if I run this, I think it'll break, because last time it wasn't handling this. And actually, you know what? I think I have to first track down the 10s, because I have 10 and 10 built in. Yeah. So what I want to do is make this like image width, or source image width, source image height, and then pop back up to 11 and 11, source image width, source image height, and then we'll just pop those in there. That way I can alter that some more in the future if I so decide to do. Now before I continue, Rupin3 is here in the chat with us and is asking, can you explain the algorithm? And I can. It's not going to be, it's a little bit, it took me a few sessions to build it out. It's a little bit in depth, but let me give you a quick introduction to the algorithm. So the way it works is, yeah, that's fine. Okay. This is a pretty old version of Milton at this point, by the way, so it's still got, like, it doesn't have smoothing right there, as you can see. We're still getting the corner thing going on where it makes little corners, but don't worry about that. The new version doesn't have that problem. But anyway, the point is, what we have is a couple of stages. The core engine of the algorithm works this way. You have some input samples come in. So you have, here are your samples. Samples. Each sample looks like this. It's a window of some kind. In this case, 3x3 windows, although earlier I was building it out of 2x2 windows. And that sample is just got some information in it, so maybe it looks like this. 1, 0, 1, 1, 0. So we have, over here, we have the sample data. Over in this column, we're going to have how frequent that is. So maybe that occurs 6 times, right? That's how frequent that particular sample should be, right? I try to make, it looks like a 2, and then I try to make it like a 1, and then it just looks like a 4. Hold on. Can I turn it? No, I can't. I can't turn that into a 1, so I'll just have to back all the way up to there so that it doesn't bug me. 1, 1, 0, and 6 in this column, right? So over here we have the sort of, I don't know what you want to call it, the data of the sample. And here we have the count. How frequently that sample should occur relative to other samples. And we just have a bunch of these, so maybe this is the first entry in that table, right? And then we have more entries, so there's an entry number 2, entry number 3, and so on. We have all these samples. And then this whole system of samples, this is the input, and then we say, we give it a block of memory basically. We give it some output, right? And that output is a nice big grid like this. Da, 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 whoop, da, 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 and so on. And that nice big output grid needs to get filled up by the algorithm. So what does the algorithm do? Well, the algorithm, at first the grid is set to be completely undecided. There's no values put anywhere. Then it, at random, chooses a sample. So step 1 is randomly choose a sample. Oh, shit. Randomly choose a sample. Well, technically that's not the first thing that happens. The first thing that happens is it randomly chooses a location in the grid, right? So randomly choose a grid spot. And this I'm going to write is, by the way, weighted. And I'll explain how that's weighted later. The first choice is unweighted. All grid spots have an equal chance of happening. Then it randomly chooses a sample. Sample. This is also weighted. And the way the second one is weighted I can explain right now. It's weighted based on the count. So this right here, this is the weight of each sample. How much we would like to put that particular sample down, right? So as I said, that's sort of used to determine how frequently this should happen relative to others. So the first sample we pick, we look at all the counts, we say, oh look, this should have, we roll a die that's basically like, say the count totals up to 100, and then when we roll a die, that's a 100-sided die, it gives us a value between 1 and 100, and then we go, okay, well the first thing is worth 6. Did we fall anywhere between 1 and 6? No. Okay, go to the next sample. We keep doing that until we go, this sample here, which ranged from 50 to 60, was the range of values that associated to this sample. This is the one we landed on, so use this sample to splat down. Right, and that's the next thing that happens is we've got a random location, we have a random sample, and then we write the sample, at the location. Shit. Shit again. Location, right? So, you put that sample down at that location, and then what you do is a process called propagate. Now, propagate is really the slightly tricky part of this. What that means is you visit all of the neighboring, so at the beginning you picked a sample, a grid cell, so maybe I picked this one, and then I put down a sample at that spot. That means I decided, okay, well this whole area here, this cell and this whole 3x3 block here, is now completely filled in, right? So I chose that one, and then I filled in all of these spots here. Well, that means I need to go tell these spots that they're not allowed to just be anything anymore, right? If I put this sample here down at this location, now this cell has to be a 1, that has to be a 1, that's got to be a 1, 1, and 1, and these all have to be zeros, which means, for instance, I can't put sample number 1 at this location anymore because this location right here has to be a 0. So what I have to do is go tell all those cells that I've just altered, hey, the possible things that could go where you are sitting has been reduced, and you need to take out certain possibilities. And what you do is you keep on propagating that, telling cells to reduce possible samples that they're not allowed to take anymore until there's nothing left to propagate, until every cell is like, look, I might need this sample if the cell next to me takes this sample, and so on and so on, and so you can't make any more progress by propagating and reducing other possibilities, right? Sometimes when you propagate, you learn, oh, this cell has to take this particular sample, it's the only one that works, it goes there. Sometimes you propagate and all that happens is you remove some possibilities, but no one learns anything else about what value they should have at their cell. So then once you're done propagating, you just loop back to here until the entire grid is complete. Now, the reason that after the propagate is done, you go back to the top and you choose a grid spot, the idea there is it's weighted because when you start, all samples have an equal probability, or all samples have a possibility of showing up anywhere. Nothing's been eliminated anywhere yet. They can all show up. After propagation is done, some cells no longer have the full set of samples to pick from. They have a subset. There's only certain samples that could show up. And so what you do is you measure the entropy of each cell. The entropy of a cell is basically how many possible values that cell could still take up, right? As you go, the entropy of cells decrease, and then what you do is you always randomly choose a cell, but you choose one of the cells with lowest entropy, right? So you don't randomly pick. It's not really a randomly choice. It's not really a random choice with weighting. It's more like the weight is such that you look at all of the things that have very low entropy compared to everything else, right? If there's something that has all of its possibilities and then two choices that have only 3 possibilities left, you take those 2 choices that only have 3 possibilities left, and you're probably going to randomly pick between one of those 2, right? And the reason for that is you don't want to, it minimizes the risk of you making an assumption over here that will contradict something over here and make it impossible to lay out tiles in between to map them together. Once you've done this, the whole grid is filled, and each 3x3 block is one sample out of that input system, and the frequency of each 3x3 block matches the frequency as it showed up in the samples, right? So this is the core engine. This whole thing is the core engine, and it's done and that works. What I'm working on now is generating samples. That's this part. At least I think it works. We might find bugs today, but I think it works. The new thing I'm doing is these samples here. I'm generating these. Generate from input image. So the idea there is I give it an input image, which is something like this, and then I go through the whole input image, taking 3x3 blocks, and I generate samples. That actually already exists too. What I want to add today is when it grabs a 3x3 block like this one, I want it to generate that as one sample, but I also want it to generate the rotations and the mirrors of this sample as samples as well. That's up to 8 possible. If you do mirroring and rotating and it lines up to a grid, there's 4 ways to rotate the original, and then after a mirror you get 1 more for that mirror, and then there's 4 rotations of that. So a total of 8 samples could come from one 3x3 window in there if you have both mirroring and rotating enabled. Okay, so I'm going to go get working on that. So the idea is, first, where's the code that turns this test-based image into extract samples from image? Wave2D extract samples from image. Yeah, so I got to reread some of this to remind myself how it all works. So, image processing params wrapped. Wave2D image processing params wrapped, unwrapped, right. So there's two different things there. Oh, you know, I'm so silly. Okay, so um okay, so there's one improvement right there. Now what I want to do is pop back up image processing params. There we go. And I want to add in some more options here. So I can tell it whether or not I want it to be wrapped. I also want to be able to tell it whether or not I want it to use rotation and mirror. So like rotate, mirror are options there, right? And alright, let me read through some of this and figure out what exactly it's talking about. So sample X positions, sample Y positions. Here it's just saying go from all the way to the end, take every possible value. Here it says stop once you start going up past the border of the right hand side and the bottom. Max sample count, X positions times Y positions. So they both agree that that's how you get max sample count, is multiplying those. Wrapped image size. His wrapped image size is 0. So what I can do is say, put that right there actually, because they're the same except for the fact that this one asks for wrapped image size times 4, but that'll just be multiplied by 0 there, and then problem solved. Now the only other thing to think about is this really the maximum number of samples? And the answer is, if it is rotated, then the params.max sample count needs to get multiplied by 4. If it is mirrored, it needs to get multiplied by 2 more. Alright, so we'll do mirror and rotate and mirror. Okay. So that should still run. Brilliant. Interesting. Not sure what that's about. Very interesting. Anyway, somehow it's generating a different thing now than it was a moment ago. You can see right here it's doing, oh, it's because I added the elbow just now? Yeah, this was out the elbow. Here I've got the elbow and it's like coming through there and then it comes through here and you can see it goes elbow and then and then you can come up here and then elbow up to here, which has a T going that way and a T right there. Yeah, it's a pretty neat map. It is a pretty neat map. And now what I want to do is, you can see it's only got elbows that look like this, right? Hello, Ginger Bill. So what I want to do is tell it to rotate the sample so that it can make all of the elbows, right? Oh, darn. Okay. Alright, so, rotation. If I tell it that I want to do rotation, I also want that to get stored in the params. So, int32 apply rotation, int32 apply mirroring. Right? And what will happen is params.apply mirroring equals mirror, apply rotation equals rotate, right? So that's not a problem. And then there should be this right here, extract samples from image. Doopy-doopy-doo. So how does this work? Extract samples from image. You give it the params and the image and the scratch memory, and then it just goes to town by taking, let's see, how does this work actually? Here it's making the wrappable image, which is nice and good. Here it extract samples from image and add to sample memory. So it goes across the image like so. At each point it is going to the source line, dest line, use repeat pattern. Right, so what we need actually here it's grabbing each one. I could either right then and there say grab out the rotation somehow, or I could say do it this way and then afterwards go through the existing samples to create rotation samples. Let me think here. How does this part work? prev sample plus equals next sample stride, repeat index. If it is a repeat pattern, so that's a repeat pattern, A putter, B putter, prev sample, current sample. Current sample. Okay, so current sample is the one we just wrote into, right? Because right here, yes. So current sample is the sample we're testing to see if current sample is already there. Prev sample is one of the previous samples, and we're saying check iterating across both of these. Check if I equals. Check if any of them are not equal. If they're not equal, then it's not. Then this particular thing is not a repeat pattern. If by the time we're done, we've gone through that entire thing, we checked every cell and they were all equal, then that is a repeat pattern. So we then go, aha, this pattern is a repeat, break out of there, and then we can either conclude to do this or that. So I want to pull this code out into a separate function first. We're going to have to do a little bit of abstracting right now, I think, because I'm going to end up reusing some of these pieces in very different ways. So in multiple places. So there we go. That should fix that, right? Oh, no. So you're going to need the sample memory, existing samples, as I should call it. Perfect. Oh, I guess that would be something like the new sample. And this thing here is supposing that that is okay. So what I actually want is something like current sample, new sample, and I want right here a uint32 sample count so that I don't have to assume that the new sample is actually at the end of the array of the existing samples. Which means I can just go like end sample equals existing samples plus sample count times params dot next sample stride. And now you're all worried that I don't have this param structure, which is true. I haven't given it to you, but I do have it. I'll just give you access, man. It'll be good. It'll be good. End sample. You're right, I'm not using that anywhere, but now I am. And now you're concerned. You're right. When I first wrote foo, I assumed it wouldn't have any arguments, so now I'm going to give it some arguments. Sample memory. How many samples are there? Very good question. Current count. That's how many. And the new sample is the one called current sample. Okay. Function foo differs in level of indirection. uint32. uint8t star. Sample count. Current count. Oh, that's not right. Current sample. Do I not have a... I don't have a total count here, do I? I can get it this way. Okay. uint 32t current count minus use count. Now you're concerned that is repeat pattern and repeat index haven't been declared anywhere, and you're right, that is a valid concern. So let me quickly reassure you that we're going to type def a struct called wave2d. What is this function even going to be called? Well, it takes in so this is like safe or sample check result, new sample check result, new sample result, new sample check result, new sample check. That's a good name for it. And it needs one int32t is repeat pattern and one uint32t repeat index. And so now I can just go ahead and go over here and say, look, the new sample check is just going to be the check result, clear to 0 that, and now it's going to complain that those things don't exist anymore, but that's quite alright. I'm just going to point out that they still exist, they're just inside the struct now. And then at the other end I can return the struct. Oh, this is going to need a new sample check. Use a repeat pattern. Right, so now what I can do is go like, look, first of all, this function here is wave2d. I'm going to call this something else. Sample check or sample check result. I think that just makes more sense. Because this function is going to be called wave2d check new sample. Wave2d sample check result equals and then boop be-do. Alright, let's see if everything still works. All I've really tried to do here is pull the code that was written right here out into a separate function, because I'm going to need sort of the generic ability to check new samples that are going to come at me from very different generation schemes than this one here, and so I'm just pulling things out for now. I might end up inlining stuff again later, but hopefully I just pulled that out with no side effects to the code, and it looks like I did. Cool. Alright, so now this right here is code for you've got a big image and you want to pull out a 3x3 block at a current location. It's basically blit, right? Yeah, so I'm going to pull that out. Because it feels like the kind of thing that I'm going to be replacing that with other options, and it just feels like an appropriate place to sort of say, that's the blit routine, pull that out into one singular concept. Wave2d sample blit. So you have basically just got to copy all that right there and then rename a bunch of parameters and things, right? Perfect. Image, so that's one thing I need, which is the image X. Yes, you need to know the X and Y positions. Image stride. Yes, that's another thing you're going to need, which is the uint32 image stride. Right, I called it the IAMG stride, but that's not going to help you because you're not a spell checker, you're a compiler. Here I will need the uint32 destin or output area. So that's just output. Params. I don't really want that. What I want is the height and the width. uint32 width, uint32 height of the output. Output width. Perfect. And now I can come in here and simplify that stuff. Good. And then I can pass this stuff in. So image, the image stride, x, y, the current sample, and the params.window width, params.window height. Again, that was just a pull a function out kind of thing. That should inline, and there we go. Or that should run the same. Very good. Okay. Finally, there's this last thing at the bottom here, which is once you have a sample you know is unique, you use this to add it there. So use count. Yeah, that's relying on the existence of this pointer here and this pointer up here, which is kind of interesting. Wonder if those want to be bundled in some way, but for now I'll just pull that out as the unbundled or pull that into a function with those as an unbundled structure. So it's going to be like wave 2D add checked sample, pre-checked sample, repeat index. Is repeat pattern, repeat index, current sample plus equals. Yeah, so that is kind of interesting. I'm not going to pull this out yet. It's one of those things that relies too heavily on local variables up here that I don't really think it makes sense to try to bundle them, and I always try to pull those things out, but this time I'm going to just say let's leave that unabstracted. That kind of exists at the level of abstraction that it belongs at. Okay. We'll just have to duplicate it or something. Okay, so the idea is now I have this code that's looping across an image, pulling out samples using this, and then checking them using this, and then adding them itself, right? Manually adding those in. Now what I'll do is I'll say perform rotations will be something where we basically get let's take the total count, and then we'll say at the very end we'll get a new total count. For uint 32 I equals 0, current count, current, right? Or maybe better, what I want to do is let's leave that the way it was, and let's get sort of a loop like the check loop from up here. When I'm checking a new sample, I get an end sample. End sample is just a matter of taking the current sample count. That would suggest I do want this up there. Sample memory, total count times the stride gives me the end sample. Okay, so I'm reading across previous samples, and for each previous sample what I'm going to do is I'm going to do a certain amount of rotation. So then what I do is I say wave 2D sample rotated sample blit, where my my source is going to be the previous sample. That's going to have a stride of params window width 0, 0. I don't really want to overcomplicate that, so we're going to call this image to sample blit, image to sample blit, and this is going to be rotated sample to sample blit. Previous sample, the amount of rotation, and the current sample. Once I've done that, I check this, and then based on the result, I possibly add it. wave 2D rotated sample to sample blit. Oops, there we go. Whoops, there we go. Doopy doopy doo. Previous sample, the amount of rotation, the current sample, the window width, the window height. Okay, so here is the source sample, here is the rotation, here is the output, here is the output width, and the output height. Perfect. So now we gotta figure out how to do this. First of all, if the rotation is 0, let me just think this through on a notebook real quick, if you guys don't mind, and then I'll tell you what I come up with afterwards. On a rotation of 0, the rule is, say I've got a 3x3 here, and a 3x3 here. Here's the source, A, B, C, D, E, F, G, H, I. Rotation. We call that the rotation X. So a rotation of 0, you just make A, B, C, D, E, F, G, H, I. With a rotation X of, let's see, 1. That's 1 clockwise turn. You have A, B, C, D, E, F, G, H, I. So with 1 clockwise turn, let's take a look at the transformation that happened. So A went from being position 1, 1 to being position, see, X is 3 and Y is 1. B went from being X is 2, Y is 1 to being, let's see, X is 3, Y is 2. C went from being X is 3, Y is 1 to X is 3, Y is 3. So after 1 rotation, Y is the previous X, and X is 4 minus the previous Y. Is that true? Let's take a look at the next row. D has an X of 1 and a Y of 2. In the rotated version, D has an X of 2 and a Y of 1. E has an X of 2 and a Y of 2, which becomes an X of 2 and a Y of 2. F has an X of 3 and a Y of 2, which becomes an X of 2 and a Y of 3. Yeah, I see. Okay, so doop-a-doo. Group. Big face for a moment. So here's what I've come up with. Right? I drew the grid. You can see it originally was A, B, C, D, E, F, G, H, I. And after a rotation of 0, nothing changes. Right? After a rotation of 1, it looks like that. And so, if I can handle a rotation of 1, if I get the right formula for that, it'll be easier to handle the rotations for 2 and 3. And all other rotations are just a modulus of 4, and then you're there anyway, so it doesn't matter. Right? So 0, 1, 2, and 3 are the only real ones. Now, looking at the transformation, I notice that this x value here, 1, 2, 3, became the y value over here, 1, 2, 3. And again, 1, 2, 3, 1, 2, 3. So the previous x value, if I had an x of 1, became a y of 1 here. An x of 2 became a y of 2 here, and so on. And by the way, this is with x going this way and y going this way, kind of down the grid, right? So if I start over here, y down, y1, y2, and y3, x1, x2, and x3, right? And the other thing I noticed is here, the x of 1, or the y of 1 became an x of 3, right? So if you were at the top of the x, you became at the far end of the y. So the formula for one rotation should be that if you have a point, x, y, the new point after one rotation is 4 minus y x. See that? So that is the rule for one rotation. Now I can generalize that 4 because that 4 is just what it takes to do the sort of it's one past the width, the size of the square. I guess this only works for squares. Now that I think about it, you couldn't even rotate a rectangle, could you? Because then, if you're trying to make it a 2 by 3 block, then the rotated version doesn't fit. So maybe you have to like sample from the image rotated. Okay, for now I'm going to assume square samples because it makes my life easier. Anyway, if it's a square, then the rotation is easy. The inversion rule is just if it's got a width of 3, 4 minus the x position. Oh, this is all in 1 based indexing, but my code's in 0 based indexing. So I have to actually do 3 minus y to get the correct result. So p x y, that's easier because that just generalizes to width minus y instead of width plus 1 minus y. Okay? So there we go. There's the corrected and generalized version of the formula. A point at x, y becomes a point at pw minus y x. Now I'm just going to quickly take some further steps there. So, a rotation of 0 is like this. A rotation of 1 is like this. A rotation of 2 is taking a rotation of 1 and applying it to itself. So that becomes w minus x, w minus y. Rotation of 2, right? Because the x value becomes the new y value, and w minus the y value becomes the x value. Yeah. And then x, y becomes the x value becomes the new y value, and w minus the y value. So that becomes w, or y, and w minus x, 3. Okay, so the rotation rules, as I see it, for all of these are here. So points with 0 rotation, a point of xy becomes a point at xy. With 1 rotation, a point at xy becomes a point at w minus yx. With 2 rotation, it's w minus x, w minus y, because you just apply this rule again, right? So the old value of x becomes the new value of y, and the old value of y gets subtracted from w at the new value of x, right? Then if you apply that again, that becomes the new value of y, and this here, if you do w minus this, you just get y, so that becomes the new x. Okay. Okay. So now that I've got my rule, we can just use that as a guiding sort of system to write this. So I could either do a switch on the rotation and then just write specialized code for each one, or try to make a generalized thing that somehow does the walk across the destination in a way that is computed right from the rotation. I think I'll just do a switch. Okay, so for case 0, we basically do this. Output width, and then we're done. For case 1, let's think here. We're going to do something kind of like this, but everything that happens with destination is now called, is now suspect, right, to being possibly wrong. So let's think this through. What happens at each step? Well, with one rotation, we want to start in the first xy actually starts at w minus yx. So, if we're starting there, how do we want to do that? Plus we're adding by line widths at each step in the middle. So what'll happen is whatever dest value we have, we're going to add the output width there, because at each step we step down one whole line, right? And the reason for that is when x increases by 1 on the source, the y increases by 1 on the destination. And then what we'll do is we'll say at each step, so this is like dest column. This just starts at dest column, and then dest column gets decremented 1. So when the y increases by 1, the column number decreases by 1 because the x is w minus y. So if the y in the source increases by 1, the x in the destination decreases by 1. Now we just need to compute the correct original destination column, which is just going to be the top right corner, which is the output plus the output width minus 1. Perfect. Or at least hopefully so. I'll have to run a quick test for this first to make sure that I like all of it. Alright, so again, I'm gonna just copy that for the next one. Okay, so now destination or rotation 2, what happens? Well, we're going to start in the bottom right corner, which means we're going to start at the position where, oh shit, source sample. Okay. So we're going to start at the bottom right. That is, we're going to start at output plus output height minus 1 times output width plus output width minus 1. Okay, so if I expand that out, I'm sure it's not, I'm sure it's going to collapse a little bit. So, boom, boom, boom. There we go. Right, okay, so output width times output height minus 1, because this gives me every cell in the output, and then if I subtract 1, I've got the last cell of the output. Makes perfect sense. Awesome. So, I start from the last cell, and, oops, I put that in the wrong spot. That should be right here. And that is, well, let's see, every time x increases by 1, which is right here, in the source, the y is going to decrease by 1 in here. So we're going to go minus output width. So that moves us down one line. And then every time the y increases, oh wait, we want to, every time the x decreases or increases, the x needs to decrease by 1. So to decrease the x by 1, just subtract 1. And that makes this the destination line. This is the destination, and then here we subtract the output width from the destination. So this one is actually pretty good in terms of cache, because it looks like it's just rendering the whole thing out backwards. Kinda. A, B, C, D, I, G. Yeah, that's what it's doing. This could be memcopy. This could be backcopy. Okay. Just notes on how to speed things up in future iterations when I'm iterating on speed, which is going to come sooner or later. The only reason I'm putting it off is to make sure I have all the features that the original has before I do that. Okay, and then for this one the rule is if y, okay, we start at 0, 0, which means we start at an x of 0 and a y of at the bottom. So we're starting the bottom left corner now. That means we're starting at output plus output height minus 1 times output width. Okay, and that's going to be a column, I'm suspecting. At each step, when x increases, y is going to decrease. So this is kind of like this, except it's a minus. Okay. And when y increases, the x needs to increase. So here we have x increasing, and we're going to turn that into y increasing. And then this right here just starts on the destination column. Cool. Cool. So now what I'm going to do is pop down here to main, and I'm going to kill 100% of the code. Alright. And I'm going to replace it with a thing that does rotation test. Okay, so the rotation test is going to go like this. I grab uint32t source, which is going to be 3 by 3, and look like this. I'm going to have dest, which is going to be 3 by 3, and that's going to look like this. Then what I'm going to do is print dest 0, 0, bloop. Wave 2D rotated sample to sample blit source rotation dest 3 by 3. Print the destination again. Doopy doopy doo. 1, 2, 3. Cache override asks, what is a wave function collapse? Question mechanic? Oh, not question. I'm sorry, I misread that. Quantum mechanics. Yeah, so wave function collapse, what I'm doing right now is I'm building a procedural generation algorithm that is a very nice way of sort of building out two-dimensional, or I guess n-dimensional, but it works, it's easiest and sort of scales well at 2. And I'm building a two-dimensional version. So I guess mine in particular one is a two-dimensional wave collapse system that basically procedurally generates nice big large two-dimensional grids, filling the grids up with values by following certain rules. So it starts by saying, alright, here's what we're going to set some value here at this position, and then it figures out areas nearby and how to make those match, and it all runs all that so that the output looks a lot like the input, except that the output could be sort of bigger and randomly sort of filled in different ways than the input, but it looks very much similar to the input. And a full description of the algorithm I actually did today at the beginning of stream, so if I post this on YouTube, which I usually do, unless something goes terribly wrong, I'll post this video on YouTube. You can go check out the description of the algorithm. Alternatively, you can just go to the wave function collapse. Let's see, I've got it around here. You can just go to this GitHub where they've implemented this in C#, which is what I'm ripping off. I've just shared it in the chat. If you go to that GitHub, they've got a C# implementation of it that works and has all kinds of examples. I'm just trying to make it in C because I'd like to make a nice high-speed, awesome sauce one. And see if I can't find some new features to pull out of it once I've done that. Okay. Now I just need to make this print dest function. uint32 dst 4. I really need to unbind that because I keep screwing that up when I'm trying to type fast. Y equals 0, y is less than 3, plus plus y, doopy doopy doo, doop, 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 good, and then printf, let's see, it's %u dst I uint 32i equals 0 plus plus I printf new line doop doopy do doopy right. Doopy doopy doo. Doopy doopy doo. Where are you? Doopy 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 doo. 'Doopy doopy doo. Doopy doo. Doop doopy 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 doo. One, two, three, four, five, six, seven, eight, nine. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Awesome. So that is my rotation test. It appears to be working. I'm just eyeballing it. So it's not really a sort of, I don't know, unit test or whatever. But it does look like it's working. So cool. And now we can go back to doing this and rotated sample to sample. Yes, that's already set up. So, and this whole thing here is if params.rotations apply rotation total count. Failed. It failed. Just because I added in rotations? Apparently. Weird. Not happy. Unhappy. So cache override is asking if I'm still in school. The answer is yes. The answer is yes. So, why does it fail now? It shouldn't be failing now. It has more options. If it has more tile options, the only reason it would be failing is if it is making bad decisions about where to put down tiles. So, well, okay, what I should do is go back to debugging and go to debug mode 3 and then run it here. Why do I not have a scroll bar? You know what? Screw the debugger. We'll just run it in here then. What I should really do is make a graphical version so that I can just see this happening at whatever pace I want and scrub around in it. You know, generate sort of a animation history and look around it. So far nothing here is going to be problematic except that on the top it put a 1 and on the bottom it's got a row of zeros coming out. So it doesn't really have any good way of handling that if it can't round the bend later. And you can see down there it's filling that out with ones more, so if it's going to round the bend, it's going to have to make that decision soon. Now you can see there's a line right there of question marks that it hasn't filled in yet. We could in theory use that, although no, it's gone ahead and filled that in with ones now. The zeros are dropping down, but if they hit that dead end, they're going to run out of options. Okay, so there it put down a new round of zeros, and yeah, it's turned that zeros. It still has a way to connect there without breaking, and there, and that could round that bend there. Wait a minute. Darn it. Let's turn those rotations back on. Alright, how's it going? Okay. Well, you can see the rotation seems to have worked because it's got elbows that look like this, and it's got an elbow that looks like this, which neither of which are elbows that look like that, which is what is built into the system. It's what's built into the input, so it's definitely rotating it correctly. But man, that's so fascinating. Look at that. So where is the contradiction going to arise? Any ideas, folks? Any ideas? I don't see any problems yet. Alright, so right there it thinks it hit a contradiction. What I need is a thing that when it hits a contradiction, it somehow draws a map of where it thinks the contradiction is. That's what I should do next. Because I'm looking at this and thinking, I don't see anything horribly wrong anywhere. I mean, it doesn't have to dead end any of these. There's no reason it should think that. Yeah, so what I'm going to do now, let's see how much time do I have. I have 30 minutes before I'm at 2 hours, which is where I like to try to keep the stream. So I'm going to... Yeah, I'm going to try to make it render a screen where it sort of X's out where it thinks errors have occurred. Um, okay, so let's see. So this is... It cannot coexist. Coexist check. Sample one. trying to understand exactly what this does. So cell 2 is finished. What does that mean? Cell 1 is... Okay, cell 1 is the one that's changed. Cell 2 is the one we're propagating to. Now what happens is we come down here and we figure out this is the area where cell 1 and cell 2 overlap, and this right here is the flag about whether or not cell 2 is already finished. It already has a single state and it can't be collapsed anymore. Potential state count. So for cell 2, T2, we check if cell 2, if cell 1. So we go across, T2 goes across all the samples and T1 goes across all the samples, and any pair of samples that both cells think they might possibly be able to use, we check and see if those two cells can coexist with that. If those two samples can simultaneously coexist. If we get to the end and those two samples can't coexist, then the coexist check failed. But if I find two samples that can coexist, I say, alright, great, there's a way for cell 2 to keep that. If I find a state for cell 1 and a state for cell 2 where they don't contradict, then I go, okay, this particular state for cell 2 is still possible, because we're already saying cell 1 has gone through its changes. We're not going to change anything in cell 1. The things that are available in cell 1 are going to stay available. But that means everything in cell 2, we got to check that there's a way that cell 2 could possibly take that state. If given the things that are still available in cell 1, cell 2 can't possibly have certain states anymore, we have to check that and go, look, cell 2 now wants to do a change because this state is no longer possible. So what we've done is we've looked at cell 2, we looked at one of the states in cell 2, we've checked all the states in cell 1 and seen do any of them line up, are any of them compatible with this state of cell 2. If any of them are compatible, then we don't need to change that particular state in cell 2. But if we get down here and that state in cell 2 cannot coexist with any of the states available in cell 1, then we have a contradiction because cell 2 is already finished, right? So this is where we have a proper contradiction where we say something like fail info.type equals fail impossible to resolve chain impossible to resolve. Fail equals 1. Wave 2D add change. Add change success already on queue. Add change success. So the only way it can fail is if it runs out of memory in this case. So this is change queue out of memory. Okay. Awesome. So if we get to the end and we have failed, when do we print failed? There it is. So before that, I'm going to say, look, if we are, debugging, and we're on any level of debugging, then we're going to consider printing out some debug info for the failure case. And the way that'll work is we go first of all, switch on failinfo.type. If the case of failure is valid sample count 0, then please printf that I guess we're not using that, so I'll just do it this way. Then please printf that found a cell with a sample count of 0. Die roll bug had an invalid die roll during sample selection. Initial add change bug had a bug trying to seed the change queue after random resolution stage. Change queue out of memory. The change queue could not push a new change onto the change queue because it was out of memory. Fail impossible to resolve. Impossible to resolve. Found a reached a contradiction where some window could not be fit. At some tile on the board. Okay, now I can find out what kind of contradiction it thinks it's reaching. And then I can elaborate on the information I need, or if it's one of the easier ones, just fix it. I'm hoping that it's impossible to resolve is the failure, because that's the more interesting one. That indicates I don't have any bugs. Reached a contradictive state at some tile on the board. Okay, so that is the impossible to resolve failure, which is the one I was hoping it was. That means that there's no bugs. There's just it's a poorly chosen set of sample inputs that's leading to or a set of like tile values that's leading to some state where it goes, shoot, I can't find any samples that I can put here that will match all of the requirements being put on by my neighbors. Now that could be a bug, or it could be legitimately true that it's reaching that state. Now to find out which, I'm going to have it print out to me the board with the spot that it thinks is leading to a contradiction highlighted with X's. So to do that, what I need is a union of structs so that I can do or impossible. I'm going to do contradiction. uint32 Excuse me. Okay. XY. Okay. So, when I state that it's impossible to resolve, I also want to tell it where is the XY of the cell that has led to this problem. And in order to do that, info.contradictions.x and y. Now I think cell 2 is the one we're propagating to, whereas cell 1 is where the change occurred. I think cell 1 is the one that's really the problem, because cell 2 is already resolved if there's a contradiction, which means it's looking at the resolved state of cell 2 and going, ah, that doesn't match any of the samples I want to put out. So it's really cell 1 that is kind of in a pickle, because it's the one that's looking at the fact that there's a resolved state nearby to it, and that resolved state does not square with any of its potential states. So the contradiction happened at cell 1, which is at change.x, change.y. Okay, so now what I need is I need the, yes, this code here. I'll pull out some of that. So, static void foo, I'll come up with a name later, and if we'll generate this function if debugging does not equal 0. And basically what I want is foo. Okay. Samples. Do 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 do. Alright, so I pass in a map, a width, and a height, and a cell finished, coefficients, a sample count, and some samples. Brilliant. And then I can do the same thing down here. So I'm going to grab a copy of this code, and we're going to put it right here, with the primary difference being that if before we go, we're going to write for blah 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 width, sample width, sample height, yes, then map yy equals y equals fail info dot contradiction dot x plus x, and then xx equals contradiction dot y plus y. There we go. And then I need to take modulos on both of those, so I'll do that down here. Width modulo equals height. There we go. And yeah, and then xx plus yy times width equals, and then I'll just put in a little ox, I don't know, e. Brilliant. And now what we'll do is we'll expand this to say, look, else if v equals ox which is the value that I believe that I have up here, then I'll printf an x. Run. Alright, we reached a contradictive state at some tile on the board. Where is my contradictive tile? Right there, huh? Oh, look, you were actually in the middle of resolving stuff you didn't tell me about last time. That's why you reached a contradiction, because right there you were going to have to hit a dead end, or oh, you were going to have to make a little kitty corner. Indeed. Alright, so now what I would like to do is play with that a little bit. So what I could do is decrease the amount of noise and see if that helps at all. Not sure that it will. Hey! So that's helping to guarantee we're always hitting lower levels of, that we're not taking things with slightly higher entropy than we want to be taking. Now, I do wonder how hard it would be to say don't do any entropy. Wait, that doesn't make any sense. Oh, I see the problem. I see it. I see it. I'm guessing the higher you set the noise, the easier it is to get a contradiction, because it will more brazenly take high entropy things instead of low entropy things. I'm a little surprised that that small amount of entropy, or that small amount of noise shift actually affects that at all, but maybe it's just random, or maybe the entropies are lower than I understood. But let's take a look at the results here. So we got elbows there, that's cool. We have an elbow here and here, which meet up right there, and there's a T shape there and an elbow there. That T shape is new. All of these elbows go in. We have one like that, one like that, one like that, and one like that. So we have every elbow type represented here. We got another one like that, and that's pretty cool. That means the rotation is working, and it also means it looks like we fixed maybe a little issue with the entropy thing, maybe. As usual, let's finish this stream up by playing with the source a little bit for the last, let's see, how much time do I have? According to that, 4 minutes-ish, but, we can play for 4 minutes. Before I start playing with this, there's someone asking a question in the chat, and I will answer that. Paulipau asks, hey Alan, is there a guide to build the DLL for 4Coder Super? I keep getting linker errors when running the bat file. There isn't really. There was one. Yeah, I guess I ended up getting rid of the README Super or whatever that was called. Or maybe if you don't have README Super, that's the closest thing I have to a guide. I plan to make a tutorial on that soon. But I can't really be too helpful if I don't know, like, what compiler are you using? I'm not sure how you're getting linker errors, to be honest, because unless you're like linking to your own libraries and things, because if you're using the built-in link line, that shouldn't be an issue, I wouldn't think, unless you're using a version of Visual Studio that I'm not familiar with, or there's a line in there that enables the Visual Studio compiler in command line mode. If you haven't uncommented that line, it might be causing an issue, but that wouldn't lead to a linker error. So yeah, I'm not totally sure what your trouble is there. If you email me at editor@4coder.net, I'd be happy to help troubleshoot it in detail. Alright, let's play with this a little bit. So we have T-shapes, we have turn in the corner. Let's add in little divots on the corners here. And let's add in dead ends. So we could do that with like I'm there's one right there. There's one right there. Ah, so you're using Visual Studio 2015. That's not the one I use, so I often get little issues there, here and there with that. So yes, please send me your information and we'll troubleshoot that. Uh-oh. What the? What the? What just went wrong there? Coefficients. Coefficients equals state coefficients. What? Does it need more memory now? Is it running out of memory? State memory size. Perfect, that's what I'm looking for. Coefficient count is 97,200, and the partition 65, 5, 3, 97, 200. Oh, yes. So I need to increase the size of the state's memory. Output size, state memory size. So here I'm doing 64K. Let's make that half a megabyte. Yeah, I mean, there's no need for you to switch to Visual Studio 2013. I prefer it a little bit, because it's the one I've already been using. What I really want to do is at some point have the ability to just compile, because I also have, sometimes I have Visual Studio 10 and GCC and Clang all have little hiccups here and there, and so keeping everything sort of happy is a little tricky, because I don't have a way to test anything, right? I don't have a way to test that I'm not screwing things up. So, like, I have a few things now that I've learned, like, oh, just don't write code that looks like this. Don't ever do this because it doesn't work on GCC or whatever. But, in general, I can't manually test every compiler because I just don't have computers to have all of those installed. And I could try to, like, install VS 2015 and 2010 on my computer at the same time as having 2013, but I don't know if that, like, that just seems like a bad idea. I don't want to mess with having competing versions on my computer of Visual Studio. So I'm going to wait until I have more Windows laptops and I'll install one with VS 2015 to test on. And in the meantime, here we have a new result. Look at this. Now that I've added those divots in the corner, that allows the rooms to sort of wiggle around and change shape all over the place. And so we get things like this that look more like caves instead of rooms. And then they have these tunnels that connect to each other, which is so cool. We've got dead ends all over the place too. Doop, 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 doop. So what you could do is first run this system and then like identify the islands, like where do we have, here's a section that doesn't connect to anything else, here's another section, identify each island, and then if you wanted to make them fully connected, you could do that just by drawing paths to connect them, drawing them in manually. But it's a really cool way to just sort of get great results for and alter your result. It's so cool how you can just alter the input and get totally different results. Like you don't have to go tweak the algorithm, you just tweak the input. So let's talk about one more possible tweak before the end of today's stream. We'll put little artifacts in the caves there. It's not actually this slow, by the way. This is because I have debugging turned on. Let me turn that off so we can play with it faster. So we got some artifacts right there. Got some artifacts right there. So cool that here it did that, and then here it did a rotated version of them. It's so neat. So neat. We'll say half the dead ends have you know, what's interesting is if I put that there, it doesn't have any sample that says a short dead end can have, or that a long dead end can have a 3. So you get kind of different results depending on where you put the 3. Put a little treasure at the end of a dead end tunnel is the idea there. It might not actually show up because it, again, I'm sort of cramming it in really tight there. Yeah, it doesn't look like it did show up. So let me do a different thing. Oh, there's one. If I tighten up these rooms so that they can't wander around, maybe it'll make a difference. Because it looks like the rooms are kind of wandering out of control and not leaving a lot of space for lots and lots of hallways, which is what I want, so that my treasures show up. There we go, now we got a treasure right here. Got one right there, got one right there. Very cool. Got one right there. So that's 4 treasures got generated, and let's see. There's an artifact, pair of artifacts right there. And it doesn't look like there's any more artifacts. None of the other rooms got big enough to have artifacts. If I put the artifacts in the top right corner like this, I'll probably get more of them. Just because then it doesn't need to be as big of a room necessarily to fit an artifact in. Okay, that's a bit unexpected and strange. Huh. So I moved the artifacts and that just caused it to like behave in a totally different way. Very interesting. I should go back to the previous one since I haven't like got a I don't have a random seed changer system. It just uses the same one every time. So now it's going back to that. Really weird. Oh, you know, it's still not free to make any decision at all it could think of with that dead end, is it? Let me put the treasure right here. See if we get different kinds of treasure locations. Changes how the dead ends show up and stuff like that too, I suspect. Whoa. Maybe this is just a thing it does sometimes where it makes one big room with lots of little artifacts. But did it make it? Oh, made a 3 there. Interesting that it was okay with, oh, that is kitty corner. So now it's putting the 3 kitty corner to that room there. Let me move that one away. You know, it's pretty tricky because I don't want it to get too crowded in the source image because then it pulls out features that I don't really intend to put in there. There you go, that's pretty interesting. What we could do is say that there's like such a thing as like a collapsed wall, so that right there looks like a dead end when you're playing, but then it's actually just a thin wall you could break once you got the right tool or something. So you got dead ends that end in treasure and dead ends that are just false dead ends. It's cool how often this succeeds now. Neato. Yeah, so cool. Alright, so that's it for today. Thanks so much everyone for coming to check it out. I'll be posting this on GitHub as always. Next time I need to get the mirroring version in there, and then I want to start thinking about speeding that up because this is a little bit slow. So get in the mirroring, and then it can basically do everything except for the tiling stuff, which I don't know. I guess I'll have to run a poll next time once the mirroring is done. But you see that? That was too slow. So I'll either next time do mirroring and tiling or mirroring and speeding things up. Because there's a lot of stuff we can do to make that run way faster. And that will be fun and interesting. So, either way, I'll see you guys next week. And bye-bye.